Okay, so we have done many things so far. We understand, uh, for example, that matrix times a vector gives you a linear combination of the columns of the matrix. Uh, a row vector times a matrix gives you a linear combination of the rows of the matrix. When you want to track multiple linear combinations of the columns of a matrix, you would multiply with a matrix on the right. Each column corresponds to a different linear combination. And if you want to track multiple linear combinations of the rows of a matrix, you would multiply by a matrix on the left. Each row would track a different linear combination. Okay. We also saw that any relationship between the columns. So, for example, if you say column 2 is column 1 times 3, or column 3 is column 1 minus column 2, any relationship like that. Okay. Uh, you can rearrange the relationship to write something like column 3 minus column 1 plus column 2 is 0. And that means that there is a particular linear combination of the columns that is equal to 0. Okay, and when there is a linear combination that is equal to 0, then you will find a matrix times a vector being equal to 0. Okay, and this vector, if the relationship is non-trivial, this vector is going to be non-zero. Okay, so there'll be a matrix times a non-zero vector that will be equal to 0. So any linear dependence between the columns is a matrix times a vector equals 0. That is how it looks like. So when we do row operations, okay, so row operations are equivalent to multiplying on the left by another matrix. So when we do row operations, we do not destroy this dependency. And when we do row operations that can be reversed, you don't even add any new dependencies, okay? Because if you do an arbitrary row operation, you could add in some new relationship between columns, okay? Simplest way to see that is like multiply every row by 0. Okay, if you multiply every row by 0, then trivially, like the matrix becomes 0. All columns are related any way you want. Okay, so but so long as you do a reversible matrix row operation, you do not add new column dependencies either. Okay, and the elimination algorithm will do reversible row operations only. Okay, so and we saw the structure of the row operations. We'll look at it a little more closely today, and we'll see how to solve equations with arbitrary equations with what we know. Okay, you already know how to solve equations and how to write all the solutions of an equation. Okay, how to figure out if there are a single equations or many equations. You actually know all of it. We'll kind of flesh it out. Okay, now so use your use the AI companion to ask you to uh, give you like different examples for all of these principles. Okay, so matrix times a vector is a linear combination of the columns, all of those things. Okay, when you use the AI companion, like I found like a new bug. Uh, it seems to get confused what course you're in. So on the top right, like you can actually choose courses. So make sure you choose 345. Sometimes it gets confused, but even then, like it doesn't give you wrong answers. It will just tell you something like, oh, we don't cover this in class or something like that. If it ever says anything like that, completely disregard it because it's kind of hallucinating now. It's making up things about what is in class and what is not in class, which can be safely ignored. What follows after that is fine. So yeah, so good. So let's look at a simple elimination algorithm. Okay, so we start with this matrix. Okay, let's try doing elimination. We are going to put together all the various pieces that we have learned right now. Okay, now when you do the elimination algorithm, where do you start? The top left, and you check if it's a 0 or a not 0. Okay, now here it happens to be a 0, right? So if it happens to be a 0, you actually don't give up immediately. You don't give up on the column immediately. You check underneath the 0. Okay, you see if you have any non-zero entry below it, right? And here there is a 1, so there is this entry. Okay, so what you do is swap these two rows. Okay, now what matrix operation will swap the rows, and where do I multiply it? If I want to swap the rows, I want to do it like a matrix operation. So tell me what matrix operation and where should I multiply it? Okay, any row operation, what do? We multiply on the left. Okay, so we multiply it with a matrix on the left. Now you're going to get back the matrix that I want is this 1, 2, 3, minus 1, 0, 0, 1, 0, 2, minus 1, 1, and 1. This is the matrix I want as the product. Okay, what's the size of this matrix? 3 by 4. 3 by 4. So what should be the size of the matrix I multiply on the left? 3 by 3. Okay, so that's because you look at the two numbers here. So 3 by 4. This 4 is here. Okay, and this 3 will be in the size of the first matrix. Okay, and for the second number in the size of the matrix, it must match this 3. Okay, so you don't have a choice there. Okay, so this should be a 3 times 3 matrix. Is everyone okay with this? Right, so I get this blue 3 goes here. The red 4 and this 4 must be the same. And for matrix multiplication to be even possible, these two numbers must be the same. Okay, so and that is how I get this 3 because it matches with this blue 3 because it's the first number of the product. Okay, now what is this 3 by 3 matrix? Now, because this is a 3 by 3 matrix, it tracks 3 different linear combinations, one for each row of the product. Okay, there's one row for each row of the product, and in the first row of the product is 1, 2, 3, minus 1. Okay, and what linear combination of the rows is that? This row, 1, 2, 3, minus 1. So this is how do you get this as a linear combination of the rows? I mean, it happens to be the second row. So, but tell me as a linear combination of the rows. So, Zihan. So this is right. So this is 1, 2, 3, 1. 1, 2, 3 minus 1 is the second row. Okay, but tell me this as a linear combination of the 3 rows of this matrix. So something like 0 times row 1 that way. Right? So you'll get it as 0 times row 1 plus 1 times row 2 plus 0 times row 3. Right? Does that make sense? Right? So is that okay for everybody? Okay. So so Jacob, what should I put in the first row here? 0, 1, 0. Okay, what should I put in the second row? 1, 0, 0. This no, the second row, the second row. What's the second row of the product? Right. So yeah, you're right. So 100. Yeah, it's the first row of the product. So 100. And what happens in the third row? 001. Okay. So this is the first operation we do. Now we find a pivot. Now you look at the top left corner, you find the pivot. Okay, so we mark one as a pivot, and you want to zero out all numbers below the pivot. Okay, so 1, 2, 3, minus 1, 0, 0, 1, 0, and 2, minus 1, 1, and 1. And what you want now is leave the first two rows unchanged. Okay, second row, you leave it unchanged because this number is already a 0. Okay, now you want a 0 here. Okay, and I want to do it with row operation. So what row operation would work? So Faith, what row operation would zero this entry out? So the new row 3 is, okay, we always do it as the new row 3 is row 3 plus or minus some pivot row. Okay, so tell me the new row 3 is row 3. Little, I think you said the right thing, but can you say it a little louder? Right, so we want row 3 to be row 3. The pivot row is row 1. So you have to do some multiple of row 1. You have to add or subtract. What multiple of row 1 will make this entry to be 0? 2. Right. So row 3, and should you add or subtract? Right. So what should this be? Row 3 minus 2 row 1. Okay, this is what we need. And what matrix multiplication will let you do that? The first row. The first row as a linear combination of these rows is, right, this row, 1, 2, 3, minus 1. Tell me as a linear combination of these three rows. No, this row. So what is it equal? So you're looking at the rows of this matrix. Okay. How do I get that row as a linear combination of these three rows? What is that equal to? Yeah. But I'm asking even more basic question. This row, how do I write it as a linear combination of these three rows? No. Yeah, you need to say something like 1 times row 1 plus 0 times row 2 plus 0 times row 3, right? So because it's already equal to row 1. So 1 times row 1 gives you that, and then you can zero out with these two. So 1 times row 1 plus 0 row 2 plus 0 row 3. Okay, that's what we are doing here. So those coefficients alone, you put it here. Okay. Okay, so the second row, how do I write it as a linear combination of three rows? Same way. Same way. This row, how do I write it as a linear combination of these three rows? Tell me the linear combination first. Don't worry about this answer. Tell me the linear combination. No, not column. We are looking at rows. 0 times Right. 1 times row 2 plus 0 times row 3. Okay, so those numbers you write here. So what are the numbers? 0, 1, 0. And the third one, we are going to do this linear combination. Okay, so this is row 3 minus 2, row 1 plus 0, row 2. What are the coefficients I write here? So for this linear combination, this is the linear combination. So row 3 minus 2, row 1 plus 0, row 2. What are the coefficients I write here? No, 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 not. It should always. So I can always. It can't be in the same order because I could write it as 0 row 2 plus row 3 minus 2 row 1. I could write it in many different ways, right? Uh, okay, and you can't arbitrarily put these coefficients. What matters is the row. This is what matters. So the coefficient of row 1 goes here. This always multiplies row 1. Okay, so tell me the coefficients I write here. Right, very good. Okay, so negative 2, 0, and 1. Right, so this will be the operation that we do. And the row that you get here is, so actually one of you, can you just use one of these companions to compute this? 2 minus 2, 1 minus 4 is minus 1 minus 4 is minus 5. 1 minus 6 is 1 minus 6 is minus 5. And 1 plus 2, right? 3. Right. Okay. So we are done with the first column. Okay, so the first column, we have our pivots. We have zeroed out all entries below the pivots. So we are done with the first column. Okay. Now we found a pivot in the first row, first column. So we move to the next row, next column. Okay. And you find a 0 here. What happens when you find a 0? Right. Look under it to see if there are any non-zero entries. There is one. Okay. So you swap the second and third rows. Oh, what is this? Okay. And what should be the matrix here? So we already did one swapping, but what's the first row? Okay, so you're going to look at this row, see what linear combination of the rows it is. Okay, so what will be the first row, Jolene? 1, 0, 0. Second row? The second row, right, very good. 0, 0, 1. Third row? No, the third row will be this one, right? So this is the product, so it should be very good. 0, 1, 0. Very good. Okay. So what do we do now? Like this is our second pivot. Very good. And lucky for us, like every number below, I mean, not lucky, like I chose it that way. So every number below it is already 0. So we are done. Okay. We are done with the second column. Okay. So we found a pivot also in this second column. Okay. So where do we move next? right? So after this, where do we look at next? What do we look at next? Next row, next column, and we find a 1 there. So this is also a pivot column. Okay, and then there's no entry below it, right? So okay, you can skip this column and you go to the next one. Okay, and here there is no next row, and so you're done. Okay, the last, all the remaining columns are free columns. Okay, so the last column is a free column, the first three columns are pivot columns, right? So this is the first round. In the second round of elimination, what do? You zero out entries above the pivot. Okay, what operation would we do? So you start with the last pivot, which is 1. Okay, and you zero out entries above the pivot. Okay, so what should you do? I mean, what operation should we do? And in fact, like I've chosen the matrix so that our computations are easy. Okay, so yeah. Okay, so row 2 is row 2 plus 5 times row 3. And to zero out the entry on top, okay, so can you put both of these into one operation? And so since we are very lucky here, you get a 0 here. So any operation with row 3 only affects this column. And we have chosen so that those entries are 0. So we know what the sum, we know what the result will be. Okay, so you're going to get 1, 2, 0, minus 1, 0, minus 5, 0, 3, 0, 0, 1, 0. And I want both these operations in my operator. Okay, so the first row remains unchanged. Okay, so what should I write in the first row here? Pardon? Okay. Sorry. Oh, sorry. Not the first row. The first row doesn't remain unchanged. The last row remains unchanged. Okay. Sorry. So what in the last row? What do I write here? 0, 0, 1. Right. Sorry. Like need my coffee. Okay. So now I want to do row 2 is row 2 plus 5 times row 3. Okay, and I want the new row 2 is row 2 plus 5 times row 3. So this is the linear combination that we'll write in the second row. So what is that? 0, 1, 5. And in the top row, what do we write? This linear combination. So this is the row 1 of the product. Okay, so the coefficients go here, and this is the linear combination. Okay, so what should I write in the first row? 1, 0, minus 3. Right, so this, everyone completely okay with this? Okay, the last thing we do is to zero out this entry. Okay, so right, and what operation will you do? Row 1 is row 1 plus 2 over 5, row 2. Right, so okay, so what I keep row 2 and row 3 as they are. Okay, so 0, 1. Okay, and what should I write in the first row of the operator? What should I write here? Yeah. And I will get 1, 0, 0, and 3 minus 2 fifth. That is 2 and 3 fifth. That is 13 over 13 over 15. Is that right? 3 minus, so this is 3 minus 2 fifths. So, right, so 13 over 15. Okay, yeah. Uh, what do you mean 5 to? Oh, no, 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 no. This is the linear combination. If you write 5 to 0, it multiplies the first row by 5. Okay, so it's going to multiply. So if you write 5 to 0, okay, it will be 5 times this minus 2 times this. Or sorry, 5 times, yeah, 5 times this plus 2 times this. Okay, you'll still get a 0 here, but these numbers will all change. Yeah. Negative 1. Oh, plus row 2. Yeah, you're right. 6 over 5 minus 1. That's right. Yeah, thank you. Yeah, thanks, Jacob. Yeah. Yeah. We multiply this by 2 fifth. Right. So 6 over 5 minus 1. So 1 fifth plus 1 5. Right. Okay, thank you. Okay. And the last thing we want to do is to normalize all the pivots to 1. Okay, now we could have done it at any stage, the normalization, because of a reason you will see. The first and third pivots already 1, nothing to do. Only the second row we need to multiply by minus 1 fifth. Okay, so what row operation does that? Okay, I want 1, 0, and I negative 1 fifth, right? So minus 3 fifth. Okay, so what operation does this? So the first row I keep as is. So what are the coefficients? 1, 0, 0. Second row I multiply by negative 1 fifth. So what do I do? Very good. Third row as is. Yeah, that's good. You guys are getting good at this. Okay. So this is our reduced row echelon form, right? And we know all dependence of columns with prior columns using this. Okay, it tells us, for example, that this is the first pivot column, the second is a pivot column, third is a pivot column. Pivot columns cannot be written in terms of any prior columns. Okay, the last column is a free column, right? And free columns are columns that can be written in terms of prior pivot columns. Okay, and so free columns are columns where you don't find any pivots, and we didn't find a pivot in the last column, so it's free. Now it can be written in terms of the prior pivot columns. And what linear combination is it? It is 1 fifth times the first pivot column minus 3 fifth times the second pivot column. Okay, in this case it happens to be column 1 over 5 minus 3 times column 2 over 5. Okay, does this make sense? This is how you read off all the information about how the columns are related to each other from this matrix. Okay. Now, any questions about any of this? Yeah. Right. Uh-huh. Uh-huh. Right. Right. So let's go. I mean, this is exactly what happened, right? So here, right? So we found a zero here, and you're asking, okay, even the next number is a zero, and this two here. I mean, instead of one, you had a zero here, right? So then you would swap this and the first column. Okay. You look for any row below that has a non-zero entry. Okay, and you can swap any of those rows. It won't matter. Okay. Remember, like we already saw, row operations will not change the column dependencies. So you're free to do any row operation without changing column dependencies. And swapping is reversible. You swap, you can swap back, right? So, okay, so very good. So any other questions? No? Okay. So now we went step by step to do all these operations. Okay. Now here is a question. I'm going to call all these operations, I'm going to give them names because I don't want to write out these matrices over and over again. This is our first elimination matrix. I'll actually write it by a different, uh, yeah, this is like this was a swap operation, so I'll say swap one. Okay. Now, this matrix was a row operation in the first stage of elimination when we are zeroing out below the pivots. Okay. Now you look at this matrix, the diagonals are all one. Okay. And every entry that is non-zero only lives below the diagonal. Okay. Conversely, I mean, in every entry above the diagonal is a zero. Okay. So these are called lower triangular matrices. Okay, so this is our first operator. This is a lower triangular matrix, L1. This was another swap operation, S2. And after that, we zeroed out entries above the pivot. Okay, whenever we zero out entries above the pivot, okay, all non-zero entries are live above the diagonal. All entries below the diagonal are zero. Okay, and just like we had lower triangular matrices, this is an upper triangular matrix. Okay, this is our first upper triangular matrix, the first operation, and this is our next one, and this is our normalization matrix. Okay, you have all these different matrices. Now, can you tell me, we started from our original matrix. The original matrix we had was this guy. Okay, we started from this matrix and we ended up with this matrix. Okay, we did a sequence of operations starting from this matrix, ending up with this matrix. Okay, I want to write this entire sequence as one equation. Right, so we did I'm going to write this on the board so you can see. The first operation we did was S1. Okay, then we did L1, and then we did another swap operation. Then we did the the two upper triangular operations. Then we did a normalization. Okay. Now, if I want to, so they're all matrix multiplication operations and you multiply on the left. Okay. Now I want to write a series of, I want to write all these matrices times this equals this. Okay. What are all the, what order will I write all the matrices? So tell me from left to right, what order should I write all these matrices? Right. So essentially what we did is like a series of operation. Each operation happens to be a matrix multiplication step. Okay. And we started with this matrix, ended it with this matrix. Okay. Now we did in sequence, we did S1, L1, S2, U1, U2, and N. Okay. That was the sequence in which we did the operations. Okay. Now tell me, how do I write all these matrices to the left of this guy so that the product will be equal to this? Pardon? That's the order. But how do I write the matrix multiplication? Where will be S1? Hmm? S1 won't be far left. What's the first operation you do? S1, right? So that is the one closest to this matrix. And then you did L1 on the product, S1 times this matrix, and so on, right? So you're going to write S1, the sequence that you did, you start writing like this. Right? So this is the operation. Now, each of these can be inverted. Okay, each of these can be reversed. How do you reverse the n operation? Right. So in the n operation, you multiplied row 2 by negative 1/5. To reverse it, you multiply it by negative 5. Okay. So in this operation, you added 2/5 times row 2 to row 1. Okay. To undo it, you subtract out 2/5 times row 2 from row 1. Right. Uh, right. So does this make sense? Right. So essentially every step of the way you can undo. Okay. But if we wanted each single operator, you can undo. Okay. If you have added 2/5 times row 2 to row 1, subtract out 2/5 times row 2 from row 1 to get back your old matrix. Okay. Every step can be reversed. Okay. Now, but tell me, if I wanted to reverse all of this, all of these operations, okay, what order do I reverse the operations? So we have done a sequence of operations, right? S1, L1, S2, U1, U2, and N. If you want to reverse all these operations, which one do you reverse first? N, right? So it's like putting on socks, then putting on shoes. Okay, you have to remove the shoes first before you can remove the socks, right? So you reverse N, then U2, then U1, then S2, then L1, then S1. Okay, when you reverse all of them, so you start from your final matrix, that is this. Right, so and we'll call this R. The final matrix, we'll just call it R. Okay, so you start with R, and reversing R, I'll call it N. I mean, if I reversing this operation N, okay, I'll call it N inverse. Okay, the notation that we use to undo the effect of a matrix is called the inverse. Okay, we'll define the inverse more formally later. But we first undo N, then we undo U. We undo U2, then U1. Okay, then S2, then L1, then S1. Okay, And when I do that, I'm going to get back the original matrix. Right? Right. So suppose there's some special cases. Uh, One of the common cases is that, or one of the things to note is that this normalization, you can actually, you don't have to do it at the very end. You can do it after you finish all the lower triangular operations. At that point, you've found all your pivots, and at that point, you're ready to do the normalization. Okay. So even though matrix multiplication is in general not commutative, that means you can't swap around the orders of these matrices. Okay. It is possible in this very special case to swap u and n, u and n. You can swap these operations. Okay. And it's not generally true, but in this very special case, okay, doing this row operation and then normalizing, or normalizing and then doing the row operations, gives you the same result. Okay, it doesn't change the result. So in this very special case, you can move the n around to come here. Okay, now you cannot move n still behind the lower triangular operations, because you need to first finish all the lower triangular operations to figure out what the normalizing pivots are. Okay, so but you can move this all the way to here, and let us assume that these swaps never happened. Okay, so then you have a bunch of lower triangular inverses times a normalizing operator times bunch of upper triangular ones. Okay, now the inverse of a lower triangular matrix will always be lower triangular. Inverse of upper triangular will also be upper triangular. Okay, so it's a neat observation. Any matrix can be written as a lower triangular matrix times a diagonal matrix, the normalizing diagonal matrix, times an upper triangular one. I'm not even writing it down because we are not emphasizing this part. Okay, but you'll find this terms about LU decomposition or LDU decompositions. All they are talking about is elimination. Okay, they're just noting that the elimination steps initially involved like lower triangular matrices, then a diagonal, then an upper triangular matrix. Okay, so right, so what is this clear, like this entire procedure? Right, so we wrote this matrix as a product of like a bunch of matrices. Okay, and what I want you to pay particular attention is that in this entire procedure, we never numerically multiplied anything. We are not even thinking that way. Okay, you're never thinking that way. You're thinking in terms of what we are doing. You're thinking, oh, you're manipulating these rows, these columns. That's what you're thinking. You're never doing, oh, this times this plus this times this. No, never. Okay, so right, so here, now tell me the answer to a different question. So in principle, what did elimination tell us? Elimination gave us all information about a column relative to previous columns. Okay, now if I ask you, uh, suppose I ask you, and I'm going to use the same matrix. I mean, I'm going to use something very similar. Okay, so if I give you this matrix equation, okay, this times this vector equals this column, and notice what I've done. I've looked at what are these just happen to be the first three columns. Okay, and this just happens to be the last column. Okay, uh, and remember also the row echelon form. The row echelon form of this is these three were pivot, and this was a free column 1/5 minus 3/5 and 0. Okay, now so tell me, does this have a solution, and if so, what? what do you read this as? So you read this as, okay, this is a matrix times a vector. So it's a linear combination of the columns. Okay, the coefficients are unknown. X1, X2, X3 are the unknowns. They are the coefficients. Okay, so it's saying, okay, this is a linear combination x1 times first column plus x2 times second column plus x3 times the third column. Okay, so on the left is a linear combination with unknown coefficients. Okay, on the right is a vector. Right, so when I say does this have a solution, it means can I find the coefficients so that the linear combination on the left happens to be equal to this column, right? So or equivalently, can this be written as a linear combination of those three columns? What did elimination tell you? Right, so elimination did tell you, because this was a free column, okay, it told you it is a linear combination of the prior columns. Okay, and the prior columns just happen to be columns here in this matrix. Okay, so and what linear combination is it? What is the solution here? One-fifth, x1 is one-fifth, x2 is negative three-fifth, and x3 is 0. Okay, you so in order to solve this set of equations or any general set of linear equations, this is all you do. Okay, stack this column onto the columns that already exist here, do elimination. Once you get to the reduced row echelon form, just read off the last column as your solution if the last column is free. What happens in a case where the last column was not free? If you found a pivot in this column, no, it means if you find a pivot in that column, it cannot be written as a linear combination of the prior columns. So there is no solution. There's no choice of x1, x2, I mean, if this happened to be a pivot column, it's not here. In a different example, if this happened to be a pivot column, okay, you would say it cannot be written as a linear combination of the prior columns. That's what a pivot column means. It cannot be written as a linear combination of previous columns. Okay, solving equations is just this. Okay, elimination actually tells you how to solve equations, right? It actually tells you more. There are cases where you may have an infinite number of solutions. Okay, so here you have one solution, and this will be the only solution, right? And we'll see why later. There cannot be any other solution to this set of equations, right? So you could have one unique solution like here. You could have no solution at all. Okay, no solution does not mean that the solution is 0. Okay, they're two different things altogether. No solutions means no choice of values for x1, x2, x3 will ever make this an equality. Okay, so you could have no solutions, you could have exactly one solution, or you could have an infinite number of solutions. There's nothing in between. Okay, we'll look into this in more detail next class, but this is the general principle to solve any set of linear equations. Okay, we'll stop here. I'll see you Monday.